Good morning, everybody. Thank you for joining our webinar today. It is the waterproofing and airtightness of timber buildings here by Rothablas. My name is Chris. I am the marketing account here in North America, covering the US and the Canadian subsidiaries. And I just want to, before we start, remind everybody that if you do have any questions throughout the presentation, please post them into the Q&A section of the Teams presentation. So if you're on a computer, on the top bar, you should see the Q&A button, and you can click that. You can type right into there. Or if you're on a phone, there's 3 dots in the bottom right-hand corner of your screen, opening up a similar menu where you can find the Q&A section. So without further ado, I'm going to pass it on over to Alexander Alvarez, our local technical consultant here in the United States. Alex.
All right. Thank you, Chris. Hello, everybody. Good morning. Good afternoon. My name is Alex, and today we're going to be talking about waterproofing and airtightness of timber buildings. So, give me one sec. Okay. So, just a small introduction about the company if you guys are new, or just a refresher. So Rotoblast is it's an international company. We range from almost all 6 continents. Here, our headquarters is located in Bolzano, Italy. But here in the U.S., our U.S. headquarters is in Allentown, Pennsylvania. We have about 70 countries with sales forces, more than 25 warehouses. As I said before, we serve about 6 continents, so that's about 100 plus countries. And like from an international viewpoint, we do over 100,000 shipments. And as a consultant myself, we also have a lot of consultants across the country as well. We deal about 10,000 consultancies, and there's over 18,000 tech documentation on our website. But here in the U.S. only, we do about 2,000 SKUs on stocks in North America. We deliver to all states, 3 to 5 days or less, and we have up to expedited delivery as well from the U.S. and Canada. And you can see here on the bottom, we have about 5,000 shipments per year. Me as just a consultant for the U.S. and my other colleague, Nilu, she's the other U.S. consultant. Together, it's about 500 consultancies per year, and we have about over 1,000 active clients. And not only that, we also have a lot of salesmen for Canada and the U.S. This is the Canadian sales force, and this is the U.S. sales force. As you can see, we have a salesperson across the U.S., always on the road from 8 to 5. And our CEO, Hannes, he's the one who's running the show, along with the sales team. And then you can see on the left corner is me and Nilu, the other U.S. second consultant. So just a small refresher to look over. But today we're going to be talking about waterproofing and airtightness. And in general, what that means is just more, we're going to be looking at a passive design, comfort living, talk about air and wind tightness, talk about vapor diffusion, condensation, talk about the materials that we sell or materials that you have to look for, and also talk about details as well. So before we get started, let's give you guys a small crash course about why we do this. You know, why we do membranes and tapes, and like why is this important. I wish this was more interactive, so I can, because I would like to ask you guys, why do we build buildings? You know, just ask you guys, why do we build buildings, and what do we want from buildings? If you were to respond to that in person, you'll probably say, we build buildings because, we want to live, we want a place to stay, a roof over our head, and what we want the buildings to be, or our homes to be, is to be safe. We want it to protect us. We want it to be, healthy. comfortable, durable, resilient, energy efficient. You know, sometimes you want the buildings to look nice and beautiful, but beggars can be a chooser. Um, so that always the case, but sometimes it might be. Also, affordability. We want the buildings to be affordable as well. Um, Again, sometimes with the house market right now, it might not be the case sometimes. And also, you want it to be sustainable. So back in the days, when we made houses and buildings, we just wanted to be durable and to protect us. As you can see this is just like a pass, one of the previous historical buildings. You can see it's not. It looks, for me, it looks like a beautiful building, but to others might not be because of the color, or it might inside might be not as comfortable as it looks. So there's always some issues with that. And but today in this era, buildings have become smarter, I would say, because now buildings have a lot more technology into it. They have ways to vent out air to make it comfortable, to 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 make the space much more wider, to um, a way to stay cool or to stay warm depending on the weather, and just be very interactive where you can just come in and the lights will turn on itself, the heat will turn on by itself. So today housing has become more smarter, I would say. And that's really important because we what we want to do is make sure that all the materials we use is also smart. It's also um, in a way it's efficient. So um, so let's say for example the membranes back before in the past, membranes, it will get the job done, but it wouldn't do a great job in doing that. So sometimes the back before, membranes used to be, provide insulation, but not a lot as today. Sometimes the membranes were not installed correctly because the experience wasn't there, research wasn't there, so somehow water can still get through. Um, but then now today, you notice insulation become much thicker. The membranes are able to insulate a lot better. Can keep a place cool or warmer. Sometimes you don't even need tapes. It can also act as a tape itself. So it's very airtight. Help for airtightness. And also, it's becomes smarter in a way where it's able to manage the moisture through vapor diffusion, or just able to let in some air in, let some vapor in and let some vapor out. Was able to adapt to the weather. So these things are really important for today because we want to make sure that like when we wrap the house, and we want to make sure we're wrapping it correctly. But um, this is just from a very small point of view. But this is also really important because this adds up to the bigger picture. So let's take a step back from the architect details, like from an architect and engineering point of view, and let's try to look at it from like a bigger picture, like I would say from an energy perspective. So um, right here on what you see right now is energy chart from the U.S. in 2023. This is on the left side. This is where our main source of energy comes from, and on the right side is where it's being directed to. So, if we look at the left side, you may notice that the main source, as expected, is the petroleum and natural gas. Those are our main sources of energy, which makes sense because if it's what we always are in use. Even if you're driving a car right now, you're most likely using gas. Or you're inside in your house or in the building, you may notice that it's using some sort of energy source, um, most likely from petroleum or natural gas. However, you may be one of the lucky ones who may be using renewable energy. It's something like it's been mentioned a lot. We want to because we want to make sure we create energy that's renewable, that we're not releasing a lot of carbon emission in the air, but just something where like is anyone can have. Um, but um, however, um, One thing that we also want to talk about is electricity, and how all the main sources you see on the left side will contribute to electricity being produced. So if we look at the bottom portion right here, you may notice that there's two parts, electricity cells to ultimate consumers, and then the bottom electrical system, energy losses or energy losses. So our main sources provide energy, provide helps produce electricity. Electricity is not formed by itself; it comes from something, and in this case, it comes from petroleum, natural gases, renewable energy, coal, or other source of energy. Um, and with those contribution, it helps create electricity. However, you may notice one thing on the top side is the electricity cells to ultimate consumers, meaning that this is the energy that's that are being given to our consumers. In this case, it could be transportation, it can be electrical grids, it can be buildings, etc. But at the bottom here, about over 50% of energy is being lost. How do we lose energy? Well, in this case, it depends. Well, it depends. But to like summarize it, to keep it general, not to go into details, the main source of loss comes from heat. You know, when you, for example, use like electricity or you're charging your computer, you may notice that your charger gets hot. That's the energy being released through heat. So sometimes um, energy get lost through the waste heat, and because of that, you're only contributing less than 50% electricity being produced to the goal, while the other 60% it's being given out to something um, that you don't need. So that is not to say electricity is bad. For me, everything people talk about electricity being the future, which is good. You know, we want to make sure it's, keep things we reduce the carbon emission. However, um, there's still our electrical system is not optimized. We want to make sure we use all of electricity. We don't want to lose anything, you know, because that's just losing that's losing money right there. So this is 2023. Before the previous report, we were actually losing a lot more energy electricity. So right now it's looking better, but um, it's not where we want it to be. It's still over 50%. So we want to make sure that we don't lose anything at all. So why is this important to mention this? Because that's we don't want to lose any sort of energy or any sort of cost. What I mean by that is that we want to make sure that the building that we're making is being efficient and sustainable. As we mentioned before, what we want our buildings to be, our houses to be. We want to make sure it's being efficient with all of the energy that is that not a single penny is being lost. So in order to achieve this, we have to look at some sort of methodology, and usually in this case, it leads to passive housing. So what is passive house? Passive house is just a way to keep it general. Passive house is a house where it's able to maintain and be sustainable on its own. And there's five passive design basic principles that you need to consider. You need to look at the thermal insulation. You need to look at the windows or doors. You have to look at the ventilation system, the airtightness, and the thermal bridging. Um, all of these five principles help with the operational energy use. What I mean by that is that this makes sure that we're not using a lot more heat, a lot more AC power. We're not using a lot more than we need to in order to keep the house as comfortable, as affordable as possible. So usually you see this in houses. Sometimes you can also see it in other things too, like for example a car. You know, a car needs to be well insulated, you know, just enough because maybe you may notice that like sometimes your car gets too hot, so you have to turn on the AC, crank it up, and then you're now using up a lot of energy. Um, Sometimes there's buildings out there where you have to have the AC on 24/7 to at least keep it cool. If you don't, you turn it off for like at least like maybe like 10, 20 minutes. You start noticing the place start heating up a bit, start getting uncomfortable. So those things are not passive, are not passive design. Those are the opposite. So um, there's a couple things we need to look at. In this case, we have to look at the air tightness. Um, so when it comes to air tightness and wind tightness, we have to consider a couple of things. So you may notice the air and wind tightness are separate, and they might be defined the same, but they're different. Wind tightness is mostly what you see outside. When air tightness in this case is what you see inside. So that can be the wind, the vapor, also heat and sound. Those things are traveling in the air. Right now I'm talking in the air. So um, that's it's something to consider as well when it comes to tightness and wind tightness because we want to make sure the place is all tightened up. We don't no air is getting out into the other room or into the other side, to the outside, and the wind from the outside coming into the inside. So tightness is important because we want to avoid any heat losses in winter or um, any coolness from losses in the summer. Um, we want to avoid any control vapor migrating into possible migrating into the walls, causing formation of condensation, and we want to avoid any um, air leakage as well, which can make the place very uncomfortable. So um, so here's the overview of what air and wind tightness may look like. The layers. For air tightness, it's mostly found in the inside. Not mostly, it is in the inside. And the purpose of air tightness layer is to prevent any air from flowing from the inside towards the outside. So, and this can be achieved in many ways. You can use this with plaster, OSB or CLT, membranes, or plasterboard as well. So this way is just like way to like prevent is to keep the place inside as cold or as hot as possible, and then wind tightness is the opposite. Is prevent anything from the outside coming into the inside. So it's the same as the other one. You can use plaster, OSB, COT, membranes, cladding, just something to prevent anything from entering inside. Um, and this is really important because, as I said before, energy, electricity. We want to avoid any uncontrolled heat losses, or we want to avoid any hot or warm air coming from the outside into the inside. Um, we want to avoid the use of having to turn on the AC every day, 24/7, or in the winter we want to avoid turning on the heat every day, 24/7, just to keep the place as comfortable as possible. So we want to optimize the ventilation system and the energy source that we're using, our electricity being used as well. And it's also, it saves us a lot of money. Our electric bill might be going up this summer, so you want to make sure that when you make your houses, or when you're making buildings, or when you're living in a house or building, you're not you're using you want to live in a place where like the energy and the energy bills are low, and you're saving a lot. You're saving yourself not only money, but you're saving yourself from discomfort. So that's from an energy point of view. And I said before, comfort as well. You want to, if you live in a very hot area, you want the inside to be not like too cold, where like you need to wear a jacket, but just comfortable enough where you can walk around. You're not sweating, you're not freezing, you're not shivering. It's perfect. Um, and also, as I said before, tightness is important because it helps with the sound and heat. So outside, you may notice there's always a lot of noises coming out, um, and it's like you live in a busy city. You hear a lot of noises coming from outside, construction, cars, people talking. You just want a place to yourself. Want to like just be silent, not too silent where maybe you might go a little crazy, but just comfortable enough where it avoids like discomfort of noises, and it helps this will help you reduce any airstream coming in or any drafts as well. And from a healthy point of view, it's also important because it avoids any mold or any condensation forming, um, or some of the air, any of the bad air quality from the city coming inside to your houses, to your building. Um, this avoids any any pollens, any powders, or any contaminants coming from the outside into the inside, from the outside into the inside, or it could be the opposite as well. Maybe you're like creating like all this toxic air in your building. I don't know for what, but maybe that's happening, and so you want to reduce that from escaping from the place. So that's air tightness and wind tightness as an overview. But also one thing we also have to talk about is thermal bridging. So what is thermal bridging? Um, Thermal bridging, to summarize, you can read the definition, but to summarize it all, it's just the weak area within your detail or in your thermal envelope. Um, it's usually what happens is like in a corner. Usually it happens in around the corners, where one place is very hot or very cold, and the surrounding area is the opposite. It's the opposite. So it's really important to avoid thermal bridging, because if we don't consider this concentrated area where it's hot in the surrounding area, it can lead to mold. And mold is bad. Mold is like some sort of fungi, some pathogen that it can release spores, and even the look at it, the look of it doesn't look beautiful. You don't want to see that in your house and in your building, and you may notice on the picture on the left. Um, so the story behind this, the history behind this, is that the person used the right membranes. They used the right membranes to wrap the building around. It was perfect. But there was one thing that the person forgot to do, was to use tape. Um, when you use membranes, you some membranes are self-adhesive, which is good, and that's really good. But also you have to consider about taping as well. Um, so you have to avoid anything from coming in and coming out, and even all it takes is the smallest gap for this to happen. Um, there was no tape between the walls and the roof or around the beam, and then what ended up happening is vapor was able to still come through, and it was able to condense around this area. And since this was a thermal bridge as well, you can see how it's concentrated around this corner on the pic on of this room, and if you, on the picture on the left. On the picture on the right, same thing as well. You can see there's only concentrated in this area, and since it's close to the window, what could have happened was that like in that corner, um, how mold formed was that, like it was like the air around it was like low, temperature was low, and over a period of time, the place got heated up, it got cold, and then the area still was able to form mold. So we want to avoid that from happening. Not only that, from mold, we don't want mold to happen. We also don't want any interstitial condensation or condensation forming within the details inside the walls, which is can be very dangerous because you don't notice this happening because um, it's like within inside the walls, and you can put dry walls behind dry walls or like some plaster at the end, but then in the inside you don't know what's happening, so maybe sometimes you have to either cut it up or go inside, and those spaces are tight. You go in there, it gets messy, and then you see the mold, and like, oh great, now we got to tear the whole wall down, or we have to fix this, and it's very uncomfortable. It's very difficult because it's inside the walls, and I would, for me personally, I wouldn't want to be inside the wall fixing that. So this happens when moisture air penetrates inside the enclosed wall into the floor cavity, and then condensation happens. So the condense it was the vapor that is able to manage to get through the detail didn't escape. So it stayed inside, and that created water, and that created a puddle of some sort. And you may notice, like, you see the wood rotting. So that's what happens. Water stayed inside the timber element, and water was able to build up, and then the timber inside now is dealing with damages. So this is one thing we have to avoid from a structure point of view on as well, because once the place start getting damaged, the the structural capacity is reduced. Now you have a reduction, so we want to avoid this from happening. So what we need to get is something that's very some sort of vapor control, something that makes sure that the vapor doesn't get lost along the way, is able to get out the detail, is able to leave, but if it wants to leave again, is able to come back and recycle, like cycle back. So we want to make sure we want that we want to get that, we want to provide that help. Um, so how does that happen? Like, how does vapor make damages? Like, how does vapor create water? Like, if if you remember the rain cycle, there's always precipitation, then there's condensation, and there's precipitation. It's evaporation, all that. I didn't do it in order, but I hope you know what I mean. But so in the air, there's a lot of vapor. There's a lot of oxygen. There's a lot of hydrogen. There's a lot of carbon, CO2. There's a lot of molecules in the air, and within that air, there's hydrogen and oxygen. And for those that may not know, water is H2O. So um, you do the math. Hydrogen plus cup of oxygen, water starts forming. And in this case, it doesn't start like a big glass of water, big glass of water that forms. It's like the very smallest droplets, or like just very small. They start off small, but over time, as this builds up, this creates a puddle, and it creates more puddle, and then now you have a lake of water inside. So just the basic understanding of it. So what vapor wants to do is that what it usually wants to travel from a very from one area to the other. So what you have in the inside, there's a lot of vapor forming, but then it sees outside and says, okay, there's a lot more space outside. It's suitable for me. So it it wants to get out, and usually gets out through the walls, through the windows, through the doors, and it this creates an issue for the walls of the windows, more specifically for the walls, because within the walls, there's maybe you're using wooden studs, and now the wooden studs have to deal with that migration of vapor from the inside going to the outside, or vice versa. So just to give you a scenario, imagine this winter, it's cold outside, and then outside it's very dry air. Then the inside, and what happens is that the vapor wants to go to that place, but it needs to go through the layers, as I said before. So it had to go through the insulation, has to go through the stud walls, had to go through um, the sheetrocks. It has to go through everything just to escape from the inside. Um, so that's nature. Uh, we can control nature a little bit. So in order to control this phenomena from happening, is that we have to make sure that we're positioning things correctly. We want to make sure that we're allowing vapor to escape as naturally as possible. So what we do is that we want to make sure that we're placing the insulation, the vapor control in the right place. So um, we from based on experience from, other salesmen, or maybe you're a contractor, or you're someone who is very experienced with like installing membranes and tapes, you know where to place them, and it's very common sense. For those that may not know, we also there's other softwares you can use as well, like Ubicus. We actually have Ubicus here in the company. So, if you're looking for a tool or you're looking for like some help, you can send over your details and we can plug them into Ubicus or Woofy as well, and we can provide you some guidance. But in general, we have softwares that can help you where to position things. You can play around with it, and you can see maybe if you were to place something in the middle, how would that interact with the detail? Would that create a lot of condensation? Would it create a lot of airtightness, etc. However, based on like practicality, you kind of have an idea where to place things, and I hope so. If you look at the picture on the top, you may notice is red, is wrong positioning, because what the person did was they placed the insulation within the walls. Um, if it might make sense to them, but what you want to do is you want to place the insulation towards the end of the wall, like whether that's the inside, towards the inside, or towards the outside. It depends on the environment you're in. But in this case, what the person should have done was they should have placed the insulation in the outside, because maybe the outside, that's the weather that they don't wanna have inside. So in this case, maybe it was during the winter time, they placed the insulation on the colder side. Um, and with that, I was able to provide some guidance for the for the vapor to escape. And what I mean by that is, if we just go to the next point. Yes, right here. Well, when it creates guidance for the vapor. So during what happens is that um, if there is vapor, like it's warm on the inside during the winter, as you want it to be, and it's as it gets warmer, and it's colder outside, the it tends to create some little like smog. I don't know if you ever seen like a window during the winter. You may notice it fogs up, and then when you try to touch it, you can feel like it's a little wet. That's what tends to happen. And on the windows, it could be okay. Maybe you don't want that, so that's not fair. But within the walls, that is something you want to avoid completely. So what the insulation does is that it helps make sure that it stays as hot as possible, so it stays consistent from the inside, and by the time it gets to the outside, it becomes cold, meaning that it becomes the weather that it is outside. And if we do that correctly, that avoids any condensation forming in the middle. We want we want it to guide it just enough to keep it consistent, just enough so that by the time it's outside, um, it doesn't create any condensation. Um, so and in the summer we want the opposite as well. Maybe it's too cold inside, but it's too hot outside. We want to keep it consistently going, consistently stay as hot as possible, so that by the time it stays outside, it matches correctly with the weather outside. Um, and so we don't want this change um, to happen in the middle. So say for example the temperature outside is 15 degrees Fahrenheit and the inside is 70 degrees. We wanted to make sure that the vapor escaping is 15 degrees outside. But if it becomes 15 degrees in the middle of the layout, then what ends up happening was there's a change of energy that happened too rapidly. And if that happens, that tends to create condensation. Water starts to form, and then the wood has become wet. And now with the wood being wet, it starts to rot, and then now you have an issue. And not only that, it becomes very discomfortable, um, uncomfortable, because um, you don't want if you're living inside, you're living and you want the inside to be as warm as possible, but now you have all this, now it's losing heat very fast. Now you gotta turn on the heater, then it gets hot, so now you're losing money. It makes you uncomfortable, but also now you're losing the heat as well at a rapid rate. So Obviously, we can control it at we can control just as much as we can. So we want to make sure it's able to we want to keep as hot as possible without the need of having to turn on the heater every time. So um, so if you were to live in a winter area, obviously you want to think about just one membrane. In the summer as well. But what if you live in an area where it's very like like you have to think about both. Like for example, in Pennsylvania here, it gets cold during the winter and it gets hot during the summer. So you don't want to keep replacing the membranes over and over. Maybe you want a membrane that's smart enough, or maybe you don't want that. You want to be very efficient with the cost. So you make details that can adapt with different seasons. That is still possible, but one of our membranes, like the climate control, which I mentioned later on, is able to adapt with the winter and the summer. So it's able to help with the uh, different type of scenarios for vapor. So um, And use so usually what you want to make sure you consider, what you always want to pay attention to, is usually in the details. The details tells you where you might see condensation, where you might see thermal bridging. So if you look at this detail in the corner right here, um, you may notice that um, it's hot on the surface on the inside, but then it starts getting colder um, once it's like in the middle. This is not what we want to see because we wanted to, as I said before, we want to make sure we keep the vapor, we keep the pathway as consistent as possible. So what you see right now is a thermal bridging occurring, where you may notice that only on the surface is warm, but then past the surface it starts getting colder, and then you see any loss of energy, and this loss of energy can create condensation inside. And since this was a wooden detail that used COT and some wooden beams, now you have that COT and wooden beam wet, and wood and water does not interact really well. So how do we stop this? Um, we make sure that we replace the insulation correctly. So you may notice the pictures on the left, those are the wrong details because you may notice that there's gaps. Um, you don't want any gaps within your details. You want to, if you were to use, this is called the pencil rule. Pencil rule is where you start at one end and then you draw a line and follow the detail. If you notice that like there's a space a space between details, then that's where the thermal bridge will happen. So you may notice that the picture on the left, there's a lot of gaps. If you were to do the pencil rule, you're gonna have to lift your pencil to reach the next detail, which is a big no-no. So on the picture on the right, you see that when you do the pencil rule, you notice that like you're still following the detail. The line is consistent. You're being consistent with your installation. Um, and then you can see at the end this is your best um, the best detail as you can because you're keeping it very concise. You're keeping it consistent. So you want to make sure that you're placing the right details. You're applying the right membranes and the right tapes, and that you're protecting it as well. Um, you see the pictures on the left, the wrong installations. You see one where like they didn't use any tapes, any membranes, or no insulation at all, and then there was a gap there, and that's where water um, came through, and it causes puddle. And then you have a picture on the right at the bottom right corner. This is the right installation because you're protecting the insulation from the top if there was a rain from the top, and you're also protecting the insulation from the bottom in case water is somehow it's able to escape through the pipes or something. So you want to make sure you're wrapping the insulation as correctly as possible. Um, and in order to do that, you have to consider a couple of things. You have to make sure you're choosing the right membranes. Um, we have three family membranes. We have the barrier, we have vapor, and we have troposphere. Um, so what are they? Um, they're membranes that use depending on what you're looking for. So if you here's just a chart of what you need to consider for the type of membranes. And it's really important because you can live in an area where it's very hot. You can live in an area where it's super cold. You can live in an area that's very humid, or you can live in an area where it's super dry. So you have to make sure one, consider the climate zone. You also have to consider the sun exposure. How much sun do you get? Sometimes some places where it's always cloudy every day, or you don't even get any sunlight at all. Um, or some areas where like the sun is 24/7, you're burning in the air, you're burning up once you step outside. So you have to consider the sun exposure and the UV uh, that it releases. Um, you also have to consider the thermal resistance and also fire reaction as well. If there was a fire to happen, how would the membrane react to it? Will it like burn up, create like this toxic fumes, or will it just burn up easily and doesn't create any fumes, but it burns easily? I had to consider that as well. Also, you have to think about the mass per unit area. How much do you need? How wide do you want it to be? How narrow do you want it to be? You also have to think about the permeability and the water tightness as well. How much vapor do you want to go through go through your layers? How much do you don't want? How much vapor do you not want to go through? And also water tightness. Waterproofing. How much do you want an area where like you want a place where like you don't want any water coming through? So there's that. So if you don't know how to choose, you can also go on our website as well. You can we have a like a filter, like an interactive map where you can see, okay, for example, I live in Florida, so what kind of memories do I need? Well, I mean, it's very common, like you would need something that's very like for a very tropical hot climate. So we will provide you um, some help with that, like which one to choose. And you can see that we provide some details here as well. It's very small right now. You may not see it, but if you go to our website, rotablast.com/climatic dash filters, um, you can have a look and see where you can find all which membranes, which family of membranes you need, what kind of tips you need, and where to place them in the inside or the outside. So there's that. Um, but let's get into our families. We have the barrier, and as the barrier say, barrier is a close to vapor diffusion. Um, it does not allow any moisture to travel. You usually see this usually in places where like it's like the first layer that you want to think about, like before your facade. Um, Maybe you want this in a place where like you don't want, maybe for example like a sauna, you don't want any heat escaping, or you in a very cold air, in a very cold room or a cold place, you don't want any cold from escaping. You may want to use the barrier here in this case. uh, However, you have to also think about like um, if what if water is able somehow get through the layers. um, Now you have water trapped inside because, as I said before, our barrier does not allow any moisture to travel. So now you have water trapped inside. So that can go for our membranes, and that goes for any kind of membranes if you think about it. There's some membranes out there that acts like as a barrier. So if you choose the barrier, think about the scenarios. Think about the worst case scenario. Think about your best case scenario, and decide. Okay, I think I want to go for our vapor barrier. Or so just to give you guys an understanding, like how that might look. Barriers are usually like the at this end right here. You can see this is our barrier right here. It's like right towards the beginning of the layer, and then right behind it, you have all the insulation, the OSB. We also have a transpire, the other type of membranes. Um, so there's that. or like on the roof as well. Maybe they wanted the barrier here at the bottom because they don't want anything. They don't want the air from the inside to escape to the outside, or vice versa. Um, so there's that. But then what if like you want something that's like like you want to be maybe very breathable? Maybe you want something like, okay, like I might get a little wet here, or might rain a bit, so I want to make sure some vapor is able to escape. That's where a vapor comes into play. You install this on the warmer side of the buildup. So maybe you live in a hot area, you want that on the outside, or maybe you live in a very cold area, or the opposite. Maybe it's like hot or cold sometimes. You place this more like most likely in the inside. They allow a greater diffusion of vapor, so that means they allow a lot more moisture to travel. Um, and so maybe that's the kind of application you want to apply. And you would see this a lot above around the barrier side, like the where you inserted your barrier. So you usually see this at the towards the beginning of the buildup or the end of the buildup, depending on where you're installing, and also depending on the climate zone as well. Uh, and you can see here vapor is right towards the end, where it's very permeable, meaning that a lot of vapor gets in and out, and that could be something that you want. Um, but maybe you want something that can do that, but can also not do that as well. So that's where the climate control comes into play. Climate control is one of our smart membranes. Um, is able to adapt to the weather. So you see at the bottom on the picture on the left, you may notice that like on the outside was very hot. Maybe this was during the summer, so you want a membrane that can, okay, I have to adapt now. I have to make sure that there's less vapor, a lot coming from the outside into the inside, so it adapts in a way, and it does this through the material of our climate control, or the chemical reactions. But then what if it becomes the winter? Now you have heat in the inside, a lot of vapor in the inside that now wants to escape from to the outside. So now you have the climate control adapting and say, okay, now I have to do the opposite. Now I have to make sure heat and vapor doesn't escape from the inside to the outside. So you have to consider that. You have to make sure you're like considering this, like what you're looking for. um, and it's also very this can also be very useful for flat roof. Flat roofs can become an issue because there's no inclination, there's no angle. So if it were to rain, water will build up on the roof, and you don't want that. Like sometimes you can have a barrier on top, so like now you have the no water going into the CLT or into the wooden panels below it, but below the barrier. But then somehow, some way, water can still get through, and so you want a way to mitigate that. So sometimes people like to use the vapor of our climate control. Other times, maybe they want to use some sort of ventilation, some vents, to let the air circulate through the roof. It all depends, like it all depends on what you're looking for. How much, if you're trying to save money, if you want to make it as easy as possible, that can adapt. You don't have to think about it anymore. The climate control might be a good option for you. And yeah, you can see here where we installed the climate control. Usually, it can act as a barrier as well, like or it's towards the middle. And here's just some more pictures of the climate control being used. You can notice that it was used in the inside on the warmer side because this was doing a very snowy area. There's no hot air outside, but it's very dry outside, and vapor wants to go from a very wet area to a very dry area because it's much more space. It can expand, it can do whatever, so it wants to escape. So the climate control is saying no. You're going to stay inside. This is where you belong. You're stuck here, and now heat up the place. So that's something to think about. Um, And the last class of family, we have the transpire. You usually lay this on the cold side of the buildup. Um, it's very little resistant to vapor diffusion. So now vapor was, it lets vapor to get in and out, come in and out. But now vapor is like, okay, now you can go in, like, I don't care. You can Vapor can just come in and out without stopping. Um, it's it can become it can act as a good layer. It it can be, breathable. It can become water tightness and wind tightness and air tightness as well. Um, and as I said before, it depends on the weather you're working in. Um, Tri-speed might be a good option for you, especially like in the places where it's just a single-sided uh, temperature. So you usually most likely see the tri-spear right towards the end or in the beginning, but it depends on the temperature as well. So like for example, right here, the tri-spear is located in the outside. So it was like a very winter area. It's a very like it's only winter only, so tri-spear is in the outside, or maybe like you're thinking about, okay, I can just use the tri-spear, then I use some other sort of layouts with it, so you can do that as well. Um, so yeah, just give you an overview of what transpire, vapor, climate control, and our barriers are like from a table point of view. Um, just to speed it up a bit, just to make sure I cover everything. Um, so not all membranes are made the same. Some membranes are microporous. What I mean by that is that it's permeable to like the very small holes within the membranes. Um, if you were to feel or like look at the membranes, you may notice that there are these very tiny holes on the membranes, and that can be important for like certain things. It can provide, maybe you want this type of material because you're limited to this. But then there's the monolithic membranes, which is not like more like physical, it's more chemical. So monolithic is like a continuous element um, that allows permeability to travel through chemical reaction. Um, and usually it provides you a much more thermal stability, more durable. It could be more UV stable, and also more resistant to more like pollutant, like more like very more toxic fumes. Um, so that can be also something to think about when choosing the right memories. What kind of materials you want? Do you want the best? Do you just want the one that gets the job done? So that's something to think about. Um, you can also show this quick video, or maybe not. Yeah, but the video was gonna show you the type of testing we do on the headquarters, from to just to make sure, just to see how the membranes and tapes react. So um, we've done some testing where we left out the membranes and tapes outside for over an year to see how it reacts. We also tested out the adhesion of the membranes, adhesion of tapes, um, how much does water go seep through the membranes, and also how does the membranes and tape react to fire. Uh, Now, as I said before, not all membranes are made the same, so you always have to think about, okay, I want the membrane that can get the job done, but can also be fireproofing, or you want a membrane that's waterproofing and fireproofing as well. So that's something to think about when it comes to membranes, and also from a long-term point of view, you want to make sure you're not leaving any worst-case scenarios out of sight. We also sell tapes as well. Tapes are made of different layers. You may think like a tape is just like adhesion and then the surface, and that's it. Um, that's like part of the basic tape you can think of. But some tapes are made differently. Some may have a release liner where you can just remove it. This can be useful, especially when like places where like, okay, you want to like give yourself like um, some time to cut out the tape, know where to place it, and then once you have one side of it stuck, you can remove the other liner and make it easy. Also, the adhesion as well. Some adhesion is different. Some are very acrylic, some are very more chemical, some are more like less chemical as well. You also think about the primer and the reinforcing layer. So like how much can it stretch? Is it very stretchable? The form is still be adhesive, and so on. So you all, we have to think about that as well, because not only this is important, like to think about the adhesion, but it's also important because it helps you reduce any water mitigation, any water from coming through. So maybe the tape you're looking for might be good for like like water from like on the surface area, but maybe once water gets on the adhesion, it loses grip, and now water still get through. You may notice that some tapes react differently to water, so that's something to think about, to make sure you're choosing the right tape as well. But not only tapes as well, you also have to think about like other sealings, like maybe you want to use a foam instead, especially for like places like where there's like a pipe. You use these foams to like fill up the gap, or sometimes you may use some expanding tapes where like they're very condensed, but over time it expands, and you usually apply this around the windows areas, the window details, which is important because if you see here on this picture, you may notice that there's this very small gap here. If it wasn't for the adhesion, the not the adhesion, if it wasn't for the expanding tape, you will have this little hole right here forever. And if water were to somehow get through, water will be here. It will puddle up, and now you have the whole window frame compromised. So you may want to use an expanding tape instead, because maybe you don't want to use the foam, because if you ever use foam, it gets very messy, or maybe something the foam isn't strong enough. So you better use a tape instead. So it's something to think about. Um, you also have to think about the conductivity as well. Maybe you want something that, or like, if you were to install a screw in, the tape can wrap around the hole, so that this is able to prevent any air, any vapor from going in. So it covers up the leakage. So the nail band, the Gemini, those are two products that you can use for this type of scenario, where it's able to um, mold into the hole, mold around the screw, so that no vapor or no there's no air gaps at all in the detail. Last but not least, also like to talk about the windows. Windows, as you know, not only are they the gateway to the outside world, you can see outside, but they're also the gateway to a lot of things. And in this case, it can be the gateway to vapor and mold and a lot of other things to be formed around this area. And so you have to consider a lot of levels of protection. We have the blue level, yellow level, and red level. Um, the blue level, in this case, will be the outside layer. Um, in this level, this is where you have to make sure that what you're applying outside is very strong and durable. You want to avoid it's very aggressive, it's very resistant. It prevents any outside weather from going to the inside. So this can be your plaster band, maybe some sort of window frame, your sills, um, or like some sort of bitumen band, like a bitumen tape. You can use that as well. Uh, the inside level, the yellow level, this is something where like, okay, now you want something that can expand and within the small gaps, because say for example the first level of defense, the blue level wasn't enough. Now you have still a little small amount of vapor going through. So what you would do is that you have to think about, okay, how do I fill up those gaps within the window frames? So you have to think about the expanding band, the sealing foam, some sort of sealing or expanding tape inside, to cover up those gaps, like to create no gaps within the details. Because as I said before, any gaps within the detail can lead to dome bridging, and we want to avoid that as much as possible, or avoid that completely. which is possible if you put in the time and the effort into making sure every small detail is enough. So that's the yellow level, and then the last layer, the last level is the red level. This is the part where okay, it will be this. It will be like what you put the inside and the outside and the inside as well. So that can be your plaster band, some sort of tape as well. Um, Also, another good tape you can use is like a flashing tape as well. You can use that at the end, and then cover it up with some sort of facade as well, or you can keep the flashing tape in the outside as well. Keep it hidden, keep it away so that you don't have to like put something on top of it. Um, and also something to also think about as well is where you're positioning the windows as well. Um, if you were to stand next to a window, you may notice that sometimes you can feel the cold air, the cold weather, like generating, and you want to avoid that. You don't want it. You want to avoid that discomfort because that just means that the house that you're living in, the building you're in, is not is isn't able to control the temperature as much. So it needs to use a lot more energy and a lot more effort to avoid that. So sometimes you see people place the windows right more towards the middle or right more towards the end. It just depends on the details and the layers how you're doing it. Um, People prefer the middle because that way you're creating less of a thermal bridge. Because I said before, any small gaps in the details, even within the walls right here, this is a big gap right here, and then goes to another detail. So there's most likely to be condensation and mold forming in this area right here. So you want to close down the gap. You want to close down the space. So the window being here might look good for aesthetic, and put you have space here to put some pots and plants and stuff. But if you don't want that to happen, you were not thinking of that, then try to think about moving the window more towards the middle, or maybe covering this up. Um, Use some sort of sills or some sort of other layups. So you can use the expand band and the foam as well, said before. There's just some products that we could recommend. Hermetic foam. Also, we have the alpha, which is it's more it's like pre-molded, right? Like it's pre-formed, like so you can use that for like covering up like in the corners of like windows that are like coming out. Um, Oops, going backwards. And it's just an example of a window detail as well. This is a good window detail right here. You can see that they use the right amount of foam, the right amount of tapes around. Um, and you may notice that like right here towards the bottom, when they use membranes, they make sure that they don't stop at the wall. They go over the sills as well, which is important. You want to keep as consistent as possible and use up as much membranes as possible. I'm not just saying this to like buy a lot of membranes. That goes for any kind of membranes, but you have to make sure you're very consistent where you apply your tapes and membranes. Um, it's also make it easy because you don't want to like go up to the wall and then you have to fill up the sills. You have to so then you have to cut a specific amount of length just to cover up the sills. You don't want that. You want to keep it consistent, wrap it around it. You have to cut so that the whole thing is in case of membrane. And it's really important because, as I said before, you want to protect the insulation from the top point of view and the bottom point of view. There's that. Um, and then this is just another example of other windows as well. This is from KF Windows. Uh, you can see here that they use our smart band and our flexiband uh, around right here around the sills. And another thing else we gotta think about is the windows itself because windows, as I said before, are the gateway to a lot of things. And windows have, depending on the window manufacturer, they can also provide you some guidance as well. They can tell you which windows are for what, and also help you consider, okay, this window can be used in a very humid area, in a very cold area. Uh, so, said before, membranes are not made the same. Also, windows and doors are not made the same. So, there's a lot of things to think about. You can see we're over an hour already. So, this is just a crash course of passive housing and waterproof and airtightness. There's a lot more to learn about, a lot more to think about. So if you have the time, do a little research about like what passive housing it is, and because um, shout out to a boot camp I did, EMU. They taught me a lot about passive housing, and they really go very into detail. So what I told you guys is just a summary, but there's a lot more to learn about. So always ask questions, be curious, and know that membranes and tapes are very difficult, especially for me because I don't have a lot of experience from a theoretical point of view, but from a practical point of view, like as a contractor, I do know like okay, I need to apply tapes here, I need to apply membranes here. So you have to think about a lot of things, a lot of experience, and over time, it takes time. It takes a lot of experience, it takes a lot of learning. So just remember, tapes and membranes, they always go together, and make sure to wrap things around and be as energy efficient as possible. So if you want to learn more about our products, we've released a new catalog that for last year. Also, we have a lot more, and also our salesmen are also trained as well to be very efficient with our tapes and membranes, and they have a lot more experience on the practical and theoretical side. So, if you have any questions, you can reach out to your salesman. But if not, you can also reach out to us as well, and you can reach out to eng.na@rotoblas.com to learn more or you have any questions. But other than that, thank you so much. Thank you for your attention, and I hope you guys have a good day.
Awesome. Thank you so much, Alex. I currently don't see any questions in the chat, but if you do have any questions, I'll reiterate one more time on the slide. You can see an email, eng.na@rothoblast.com. If you think of any questions in the next 10 minutes, hour, next day, week, or month, feel free to reach out at any time. Um, we do have some more webinars coming up for the rest of this month and into September. But our next 2 weeks are wall to a window connection um, and fall protection systems. So until we see you next, enjoy your week.